Okay, now if you really want to understand the difference between conformation and configuration, here are two pictures that's going to explain it all. Okay, so first, conformations or conformers are actually the same compound which is going to have different orientation in space, which is going to be arranged differently in space. Say, for example, in the anti-conformation and the gauche conformation, you can actually switch to anti-conformation and gauche conformation just by rotating the carbon-carbon single bond. And since they are actually the same compound, they cannot be separated. So you cannot definitely separate from one conformant to another. And there might be some conformations or conformers which can be more stable than the others. And at any time, like if you want to interconvert from one conformation to another, you have to just rotate along the carbon-carbon single bond. Now, when you come to configurations, these are actually two different compounds. Uh, we talked about the cis and the trans isomers, they can actually be separated because they have different physical properties. They had different boiling points and they had different dipole moments. And by some means, they can definitely be separated. And at any point, like if you want to interconvert between cis and trans configuration, then you have to break the bonds to do it. Okay, so these are the differences between conformation and configurations. Okay, now let's go to the concept of chirality. What is chiral? What is chirality? Okay, so to explain that, we need to know what are chiral objects. Chiral objects are non-superimposable mirror images. Say, for example, if you want to take your right hand and try to superimpose on the left hand, it's not going to be possible. And that's because of the handedness. And similarly, your right ear is not going to look exactly the same when you look at it in the mirror. Okay, and again, it's because of the handedness. So chiral objects are objects which are going to produce non-superimposable mirror images. Whereas achiral objects, they are going to give superimposable mirror image. So if you take a fork and then put a mirror by the side of it and look the fork, it's going to look exactly the same, meaning that they are identical compounds. Okay, so these are the main differences between chiral objects and achiral objects. So just as we have objects to be chiral, there are molecules which can be chiral too. And for molecules to be chiral, you need to have an asymmetric center. Now, what is this asymmetric center? Asymmetric center is also called as chiral center, in which a carbon atom has 4 different atoms or groups attached to it. Here is an example for it. So take 2-bromobutane. Okay, when you look into this carbon right here, it's actually connected to 4 different groups. So it is connected to hydrogen. Okay. It's connected to hydrogen, and it's connected to an ethyl group, and it's connected to bromine. It's also connected to a methyl group. So you can see that there are 4 different groups around that carbon, around that sp3 carbon. And therefore, it is a chiral center, which is normally denoted by an asterisk symbol. Okay, so here is another example for a chiral molecule. Okay, so if you look into this carbon, okay, it is again connected to 4 different groups. You have H on one side, and then methyl group on the other side, and ethyl group, and here you have secondary butyl group on the other side. Okay, so these are examples for chiral molecules or asymmetric centers. And for a molecule to be chiral, you need to have an asymmetric center. Okay, here are some more examples. Pick compounds with asymmetric center. So remember, for an asymmetric center, you need to have a sp3 carbon, and the 4 groups should be different. Okay, so let's analyze this compound, this very first compound. Okay, so this is an sp3 carbon, sp3 carbon, sp3 carbon, and sp3 carbon. But which one of these is going to be an asymmetric center? Okay, so here you have three exactly same groups to it. So definitely this is not going to get qualified for a chiral center. Again, here you have two hydrogens, and that's not going to get qualified for a chiral center. But when you look into this carbon right here, it is attached to four different groups: hydrogen, Cl, methyl group, and on the left side you have an ethyl group. So this carbon right here is going to be an asymmetric center or a chiral center, and therefore this molecule is going to be a chiral molecule. Now let's analyze the next compound. This is ethyl alcohol. Yes, you do have sp3 carbons on it. These two are sp3 carbons, but then like when you analyze the different groups, you only have you have exactly same groups on it. So therefore there is not going to be any chiral center in it. Now let's go on to the next one. This is not a chiral center, not a chiral center, not a chiral center, nor a chiral center. But look at this carbon. It is going to have hydrogen. This is the methyl group, methyl group. So you have two methyl groups on that carbon, which means it doesn't qualify for a chiral center. For this one, if you look into this, this is going to be a chiral center because you have an NH2 group here, a methyl group here, a hydrogen, and also this group right here. So therefore, this is going to be a chiral center. Okay, here we have tetracycline, which is a broad spectrum antibiotic. And let's identify the chiral centers here. And remember, for a chiral center, it has to be an sp3 carbon, which is connected to four different groups. Now, if you analyze the different sp3 carbons, we can tell definitely that this is not going to be a chiral center. This is not going to be a chiral center. This is not going to be a chiral center. And this one is not going to be a chiral center because you can see that there are two hydrogens on it. But the rest of the carbons, carbon 3, 4, 6, 7, 9, all these are chiral centers. So you can see that there is a total of 5 chiral centers in this molecule, and therefore tetracycline as a whole is a chiral molecule. Okay, in general, when you take a molecule which has one asymmetric center, it is going to lead to 2 stereoisomers. Now, why 2 stereoisomers? Remember, when you put that molecule and then look that molecule in the mirror, it's going to produce the mirror image of that. So basically, there are 2 stereoisomers. So the general formula for finding the total number of stereoisomers is given by 2 to the power of n, where n equals the number of chiral centers. So if there is one asymmetric center or chiral center, it's going to be 2 to the power of 1. That's going to be equivalent to. And if there are 2 asymmetric centers, which means if there are 2 chiral centers in a molecule, then it's going to lead to 4 stereoisomers. And if there are 3 asymmetric centers, it's going to lead to 2 to the power of 3, which is going to be equivalent to 8 stereoisomers. Okay, so here is again like an explained version of the number of isomers. So you can see that this is 2-bromobutane again, and when you put 2-bromobutane in the mirror, you can see the other non-superimposable mirror image of that. Okay, and these together are called as enantiomers. So basically, enantiomers are non-superimposable mirror images. Okay, so here is an achiral molecule, and now why it is an achiral molecule? Do you see that there are 2 exactly same groups on the carbon, and therefore this is not going to be a chiral center at all. So this carbon is not a chiral center at all. At any time, like if you put a mirror close by and look at that compound on the other side, you will see that to be exactly the same compound, which means they are identical. Okay. Remember, chirality is the property of the entire molecule. Okay, now let's look into the difference between asymmetric center and stereocenter. Asymmetric center, also called as chiral center, is a carbon atom which is actually connected to 4 different groups or atoms. So here you can see that this is a chiral compound, and because of the presence of the asymmetric center or the chiral center, where this carbon is actually connected to 4 different groups. Okay, stereocenter is basically an atom at which the interchange of 2 groups produces stereoisomer. So here is an example for it. So in our cis and trans configuration, we have seen that you can interchange the 2 groups to convert from cis to trans configuration, or vice versa. And say for example, at this carbon, if I'm going to interchange these 2 groups, this original cis configuration can be changed to trans configuration. And because this is the place where the interconversion takes place, it is actually a stereocenter. And similarly, I can do the same thing on the other carbon. If I'm going to interchange this, then I can arrive at the trans configuration. So this is a stereocenter, this is a stereocenter. And similarly, when I look into the cyclic compound, which is actually an sp3 carbon, these are 2 stereocenters that we have, and we can switch the bonds here to get to the other stereoisomer. So in general, stereocenter is a general term that is used for an asymmetric center or an sp2 carbon of a double bond, which is that, or an sp3 carbon of a cyclic compound, which are these. So all these are stereocenters. All these together are stereocenter. But keep in mind, all asymmetric centers are stereocenters, but not all stereocenters are asymmetric centers. Okay, now let's do an exercise here. How many asymmetric centers and stereocenters are present in this compound? Okay, let's take the first compound. So on here, remember, if you want to determine all the stereocenters, you needed to look into all the asymmetric carbons and the sp2 carbons, which has a double bond, and the sp3 carbon, which is present in a cyclic structure. So here in this compound, we do not have any cyclic structure, so we'll not be worried about it. We'll just be looking into the chiral center and the sp2 carbon, which is on a double bond, which is in a double bond. Okay, so let's go ahead and get started. So this carbon right here is not going to be a chiral center because it doesn't have 4 different groups on it, but this carbon is. Okay, so this is a chiral center, which means it is also a stereocenter. And when you look into the next carbon right here, it has a double bond, and actually it's connected to 2 different groups, for which you can assign the cis and trans configuration, and therefore this is a stereocenter. I'm going to write it as stereocenter, and this is also a stereocenter. So we know that the asymmetric centers are also stereocenters. So basically there are 3 stereocenters, and out of which one is an asymmetric center. Okay, with 1 asymmetric center.